Okay, Assalamualaikum and good morning. So we'll continue with our lectures. So I think I want to clarify a little bit some of the things that got confused last lecture is with respect to this idea of canonical momenta. So if you look at this essentially the mistake is actually here. This is actually a plus. So please make this correction inside your notes. There are essentially two sources of confusion. So here one should remember that this is just your magnitude of the charge. Okay, charge, which in this particular case is E, which is no, because its magnitude is greater than 0, so charge of electron then will be written as because it's the charge of electron is negative, so the charge of electron is written as minus E. So this is just two different sources of confusion. One is this correction here, and the other one is with respect to this the symbol that one use. In some books they put Q, but also even Q has it's problematic later on because we are going to use Q as your generalized coordinate. But okay, I hope that settles that, and we should move on to the next lecture, which talks about field variations. Before we do actually the fields themselves, we are going to look at one intermediate example, which is the case of a string. Okay, so here in this case it's just a normal string. It's not the string theory that no. I mean, it's the basic ideas are the same, but this is not the string theory that people always hear in high energy physics. Okay, so this is just a normal string, so it's being stretched, and then essentially the string can sort of vibrate, so make displacement. So the string will be considered here of length L, and then of course it will carry a mass. Okay, the whole string will carry a mass, but to consider the intrinsic property here would be the density, which is going to be mass per unit length. Okay. So the idea here is we're going to from the idea of particle. Okay. Particle will have coordinates q. Okay. Now what's happening over here in the case of a string, there will be within the string you can consider that it's a collection of particles. Okay, so string will be considered as collection of particles along the strings. Okay. So we need to be able to describe each of these collection of particles in the string in a way that you use each particles in the string will be given a unique what you call a unique position coordinate, just like your particle. But particle here is a point particle, so there's only one particle involved, so this is single particle. So here will be a collection of particles. So how we're going to describe this collection of particles is to do a kind of approximation. So you start subdividing your string into segments. So you divide your, in this particular case, we're going to fix the string between, say, from 0 to L over here, and then you divide your x-axis that will later involve the position of the particles along the string, vibrating or whatever, displaced from the x-axis. So the idea is to divide the x-axis itself into intervals of length delta xi. Okay, so here again, your q, okay, your q will be the position coordinates of a particle on the string. Okay, so once you have this segmenting of this x-axis, which essentially trying to describe the vibration of the string, so one could essentially sort of focus in a infinitesimal approximation over here to a particular interval. Okay, so here one can think of this as qi. Okay, so you can think of this representation of this qi being given by a segment of the string, and in each of these segment one considers a Lagrangian. So here the ith segment you talk about the Lagrangian, the ith Lagrangian, which correspond to some functions which depends on the coordinates of that interval, plus no possibility of essentially because there will be some dependence on how each individual particles move along the string. So here there will be dependence on the segment one before, which is the qi minus 1, and the segments after it, qi plus 1. Okay, so this is in particular you think of your string to be continuous. Okay, string continuous. So in other words, what's going to happen is that the individual segments along the string will somehow influence each other due to this continuity of the string. Okay, so that's why we're going to have this particular part, which is not the ith segment, but the one before it and the one after it. Okay, so it will depend on that position of the ith segment and the I plus or minus 1 segment. And again, just like the particle itself, it also depends on the velocity. Okay, and because we are approximating the segment, this will be multiplied by the length of the segment. So here is the length of the segment. Okay, and the functions that one needs to differentiate from this is the Lagrangian. There will be another function that depends on this so-called variables inside it. Okay, and this function that correspond to the Lagrangian before, this is called okay, so here this is called the Lagrangian density, because this depends on the segment. Okay, just like you have your density rho depends on this the segment, so you have the mass, for example, being described per unit length or per unit segment in that particular case. So what we're going to do now is essentially to make this segment as small as possible. Okay, so in other words, your position on the segment before and the segment after will be just a linear deviation from your from the ith segment. Okay, so this is the position of ith segment, this is the position of the I minus 1 and I plus 1 segments. Okay, And how they are related to the ith segment case is by just a linear term in the length of the segment. Okay, so uh, this is just a linear approximation here. Okay, and what multiplies this length of the segment will be this derivative of q with respect to x. Okay, remember your q is a function of x. X is your independent variable here. Your q will be somehow depend on this particular x. So you have a partial q, partial x along the ith segment. Okay, so in other words, this is just like your slope at this particular point. Okay, slope dq dx. Okay. Right. So once you have done that, now what we need to do, so here is essentially a Lagrangian of ith segment. Then you need to sum over all the segments that you have made onto the string. So you sum over I, Li. So in other words, what one needs is to sum over all these Lagrangian that depends on this ith segment variables. Okay, but now one thing that we have done in terms of approximation here is the fact that qi plus or minus 1 will now be given by this deviation from your qi. So you still have your qi, but now it will depend, this one, okay, this part is going to be replaced by the derivative of the ith segment with respect to x. Okay, and then again you still have your velocity. Okay, so now, as I said, we want to make this as small as this segmentization of the string as small as possible. So in other words, you make it infinitesimal. Okay, you can see a strand of hair here when I'm scanning. Okay, so here you can make it infinitesimal here, so you put it as a dx. So once you make it infinitesimal, then this sum will change to an integral. Okay. So essentially, what do we have here? Then you'll have the Lagrangian density as a function of q, replacing your qi before, and then your derivative of your q with respect to x, and then your derivative of q with respect to time. Okay, so that's how we're going to be able to describe your string in this context of, say, Lagrangian mechanics. The other thing that we want to do is perhaps to how we're going to describe. Remember, your Lagrangian is supposed to be t minus v. Okay, so we want to know what's your kinetic energy in this particular case, and then what will correspond to your potential energy. I think the easiest thing to do is to look at the kinetic energy that comes from your q dot. Okay, so that is essentially, remember that, okay, over here I have your kinetic energy previously in terms of point particle. Point particle are given by mq dot square, the half there. Okay, so here is given in terms of mass because you have only one single point. So now these are going to be replaced inside the string by your rho, which is your density, and density here, please recall, is actually mass per unit length, so you have to multiply by the length, which is given by dx. Okay, so in other words, you multiply rho and dx. Okay, that will give you rho dx. So here the dimension is essentially your dimension of mass. Okay, so that settles your kinetic energy. Now for your potential energy, remember the fact that all these segments of your string are going to be related to with each other, so that sort of produce some form of potential energy for each of the individual particles inside your string. And how do we do this is to consider the length. Remember that you need continuity of the string, so you consider the length of the string. For example, in this particular picture over here, so we need to be able to describe all this displacement. Okay, so you consider the derivative over here multiplied by your dx to show the vertical displacement. Okay, and this will be just your interval. Okay, so and using remember that what we need is to describe a particular length of the string. So this is dl, so you just simply use your Euclidean length. So you have your horizontal square plus vertical square, and take the square root. That will just give you the length of the string. Okay, so over here then you can sort of bring out your dx as a common factor in both terms over here. So you bring it outside, so you get dx, and then inside your square root over here will be just 1 plus the derivative of q with respect to x square. But now what we're going to do is to make an approximation. Okay, for small dx, you can actually do this by taking the power series of this square root. So when you take the power series, this becomes 1 plus half qx square. Remember, this is the derivative here. Okay, 1 plus half partial q partial x square times dx, and this will actually approximate the length of the string for small dx. So you can actually see over here this term over here, because you remember that you want to talk about the displacement of the string. This term over here can be thought of part of your potential energy. Okay, so this term will be multiplied by a tension. Okay, and let me see how to think about this. This tension is essentially force per unit length. So I have a force per unit length, and then I have the slope, which is, in this case, the slope is squared. So I have 1 per unit length square. Okay, so this is going to be multiplied. Then the last multiplication will be the dx. So I get my force. Yeah, over here I have to remember what's I need the essential idea is I have to have the dimension of energy. So probably this is not force, this is probably energy. Okay. So then what happens with this tension sort of give you the right dimension for energy. Okay, so so we just accept that no, it sort of multiplies this term that sort of gives you the vertical displacement over here by this multiplied this with this particular t, which we call as tension, in order to get your dimension of energy. Okay, so once you do that, then this can be thought as your potential energy. Then you can actually write your Lagrangian by the kinetic energy minus the potential energy. Okay, so I hope that's not too much of a problem. Okay, so but now what happens over here is essentially you are doing the Lagrangian itself is doing an integral over the length. Okay, so over here, remember the action itself previously was, yeah, your action is previously was just L dt, but now your L itself is going to be integrated in terms of your Lagrangian density. So you have dt dx. Okay. So in other words, over here, then no, everything is now, instead of being written in terms of your L over here, this is your Lagrangian. This is now written in terms of your Lagrangian density. Okay. So what one need to do is remember the principle of minimal action or extremized action is to have delta I equals to 0. So rather than having your varying with respect to varying your action with respect to your variables inside over here, now remember that your variables now involve an extra thing, which is your derivative with respect to x. Okay. So let's do that. So here then you'll find that, okay, you do the variation. Okay, look at each variable is inside your Lagrangian density or inside the integral here. So you have partial L, partial Q, delta Q, okay, and then partial L, partial QX, and then this is really delta QX. Okay, so delta QX is written as delta dq dx. Okay, and the other thing will be the velocity. Then you have partial L, partial Q dot delta partial Q partial T. Okay, so you have Q dot delta dq dt. Okay, so like before, no, we would like to have your variation of your Q to be a common factor in all these terms. Okay, so if possible, you want to put it delta Q over here. Okay, so that you get something times the variation of your Q. So we need to look at these individual terms. For example, over here, it's not delta Q here, it's delta QX. Okay, so what do we do in this particular case is to think of this to be equals to the x of delta Q. Okay. So in other words, what I need for this particular term is to remove this derivative. from acting on delta Q by using integration by parts and remove this to be operating on your partial L, partial QX. So this is what's happening over here. Okay, so you have partial L, partial QX, delta dq dx. Okay, so I want to remove this d dx so that it acts on this rather than it acts on your delta Q. So you do integration by parts, and then what happens, you have a boundary term here which depends on the total derivative of the whole thing minus the derivative of your partial L, partial QX, and then delta Q. So we have essentially removed the derivative on your delta Q. Okay, but then we have this extra term. So this extra term will be when you integrate this with respect to x, okay, this is now derivative of x. So we'll just be evaluating this what you call quantity here in the bracket here at the endpoints. So the endpoints will be 0 and L. And essentially, I've forgotten to mention, we are going to fix those points. So remember, this is just like your vibration of a string. So you fix your point of the string here, and you fix the point of the string over here. So when we do the evaluation of this boundary term, okay, you evaluate your delta Q at L and delta Q at 0. And since this is fixed, your delta Q at this endpoint is fixed, so that there's no motion at the endpoints. So that means delta Q equals to 0. So when you evaluate this, then you find that at these endpoints, this is just 0. So you remove totally this boundary term, and then you're left with this thing. Okay. The time derivative is just like before. Again, you want to remove the ddt on your delta Q. You can remember that this one. So this can be thought of ddt of delta Q. Okay. So again, the story is the same thing. We just want to remove that derivative on delta Q. Then you need to do again another integration by parts, and again we fix your delta Q at your initial time and final time to be the variation here to be 0. So you remove totally the others boundary terms. Finally, what's left inside your variation over here, okay, this, and then we have transferred the derivative of ddx here to that, and then derivative of your variation here to that, and what's left inside is essentially this thing. So now everything is multiplied by your delta Q. And delta Q here is an arbitrary variation. So in order for you to extremize this so that you get delta I equals 0, then essentially what you need to have the whole thing in bracket over here to be equals to 0. So you can see that in this particular case, because of the new dependence, you have an extra term inside your Euler-Lagrange equation. Okay. The one that we had before was just, you have the derivative with respect to Q, and then your time derivative of your Lagrangian before with respect to the velocity. Okay. So now we have an extra thing which depends on this derivative of your Q with respect to x. because of the extension of your string. So let's look at a particular case. The case that we had before was to think of your kinetic energy given by this rho q dot, and then your potential energy is now written in terms of a tension times this qx squared. Okay, so if you take the partial derivative of L with respect to Q, okay, this curly L is your Lagrangian density now. So I'll just say L at the moment. So partial L, partial Q, there's no Q here, so it's going to be equal to 0. Okay. The other assumption that I have to make is rho is constant. Of course, in your string, your rho could be changing from point to point, but no. For simplicity, okay, we say that your density is the same throughout the string. Okay, so in other words, when you take the derivative with respect to q, it doesn't operate on this row because it's just a constant. Okay, so next thing is partial L partial Qx. So partial L partial Qx, if you look at the Lagrangian density, your Qx is actually appears here, so you can take the derivative of that, so that gives you minus t Qx, and then partial L partial Q dot for this one over here, then you have rho Q dot. Okay, so you plug into this Euler-Lagrange equation, then you have t times partial Qx partial x minus partial derivative with respect to time of rho Q dot. Okay, and that is simply remember that your Qx is simply partial Q partial x. So now you have d dq, so d dx qx. So that will give you a second order derivative. Okay, and similarly for the case of d dt q dot will give you a second order derivative with respect to time. Okay, so one can get this equation out from your Euler-Lagrange equation. Okay, if you look at this equation, probably you would not recognize it, but let's rearrange this equation so that your constant over here multiplies your term over here instead. So you get this second order derivative of q with respect to time minus something times partial derivative of q second order derivative with respect to x. And this is just like, if you remember, del squared minus d dt square of some function that we have seen before. So this is essentially your wave equation. Okay. So this is really your wave equation, but now it's one-dimensional. Okay, you don't have that del squared there. So and you can see that, remember your wave equation over here, usually we have, for the case of light, you have 1 over c squared there. So that is essentially whatever multiplies your derivative, the time derivative, I should have the other way, okay, but never mind. So so if I convert that, I should be writing c squared del squared minus d dt. Okay. So here then whatever multiplies your partial derivative, essentially the velocity squared. Okay. By this analogy. So in other words, over here, the one that multiplies the second order derivative with respect to x will be essentially your velocity squared. So in other words, the velocity is now given by square root of t over rho. So again, you can check that this is dimensionally correct, provided that your t times your q at squared here will give you the dimension of energy. Check dimension. And for this one, you know how to solve wave equations, so you get a propagation of wave to the positive x, and then a propagation of wave to the negative x. Okay, so here you can write it. I think this should be plus. Okay, so again, these are just things that you have seen before. And if you subject a boundary condition, say, remember you have your fixed condition between the two strings. Okay, so what's going to happen is that the kind of equation that you have will be just for your standing wave. Okay, because you need to fix the boundary condition. So that's essentially just an intermediate example how to define variation of action when you have other dependence besides your time derivative. Okay, so in this case you had earlier I mentioned about this qx thing. Okay, so this is really an example of a one-dimensional field. Okay, one-dimensional field because essentially your string here, okay, it essentially is a field that depends on x. I hope you can read this. Never mind. No, you should be able to understand. So in other words, it depends on this. It depends on this independent variable of x. Okay. Unlike the case of a particle, it's just a zero dimension. Here now you have a one-dimensional case. Okay. So now what we're going to do in order for us to talk about fields in general, we'll consider a function rather than just a function of x. Previously, your q as a function of x and t before. Now you allow it to depend on your other variables in three-dimensional space. Okay, so this is now 3D position, and then of course also depends on your time. Okay, so this will now be considered as a field in three-dimensional space, and also you also have the time variable. Again, later on we need to integrate this because what one needs to do is because your time will be just part of your four-dimensional position, so to speak. Okay, so in this particular case, it's still not relativistic as yet. Okay, but we are getting to that. Okay, so you think of these fields sort of like making in the case of your string earlier, making displacement with respect to certain direction of x, y, and z. Okay, so we can talk about the variations of these particular fields. And of course, you can even have multi-component fields, meaning you have several different fields considered. So I can have n fields here. So phi 1 is one particular field, and then phi n is another particular field, and each of these depends on R and T. Okay. So then later on, these fields will be used in terms of our formulation in terms of as a vector fields. For example, vector fields will have for a three-dimensional case, we have phi1, phi2, phi3. For tensor fields, you have more. In the case of, say, a covariant rank 2, then you have essentially 3 times 3, so you have 9 components of your fields. Okay. But again, these are just complications to say that, okay, we can have all this idea of vector fields and tensor fields being just considered as a multi-component fields. Okay. So with respect to this idea of fields now, just like your strings before, okay, string is just a one-dimensional field. Now we can talk about this multi-component fields considered on three-dimensional space-time. Okay, so again you postulate the action principle, so you need to extremize it. And like before, okay, your action is really the integral of your Lagrangian times integrated with respect to time. Okay, but when you do in terms of this fields, then you have all these new terms like your previously was qx for the case of a string. Now you have your phi a to be taken the derivative with respect to the different say x, y, z position or the three-dimensional position. So this phi a comma I is really partial phi a partial xi, and of course you also have this one would be phi a dot is partial phi a partial t. Okay, and like before, there must be some boundary conditions that one meets. So in this particular case, when you make this variation of the action, okay, then you, even though it depends on this, remember we can do a partial integration. So in the end, it will just depend on this variation of the fields. So this variation of the fields will have to be fixed using a boundary condition, so that at fixed time, say the final the initial time and your final time, that variation is going to be equal to 0. Okay, so that just saying that, okay, you consider the field sort of evolving from an initial time to a final time. But at the initial time and final time, you're going to have your variation to be equal to 0. Okay? Just like the case of your position previously. Instead of position, now you have a field. Okay? So again, when we do the variation, you have all these things coming in, okay? Because that your Lagrangian density depends on this partial derivatives here. And again, one needs to remove the derivatives on your variation of your fields. So you do a partial integration. Okay. So your partial integration here, for example, this is with respect to spatial coordinates ddxi. Okay. So remember we have Gauss theorem. Say you integrate this derivative, the total derivative, inside your volume integral. You can convert this volume integral into a surface integral. Okay, and that gives you this. Okay, so there will be a normal to the surface. So here the surface can be very general. So I have a normal vector here. So you can think of this normal on this particular, you have a volume here, and then I have a surface so that bounds the volume, and normal to this surface will be this normal vector. Okay, and what we need in this particular case, again, just like your time boundary condition, you have a boundary condition on the surface as well. Okay, so in other words, we will want this field variation on the surface to be equal to 0. So in other words, once we do this, once we fix this, then this term will just give you 0. Okay, and you are left with that. Okay, and similarly for the case of the time derivative. Okay, so that we already mentioned earlier. We want to fix your field variations at the initial time and then your final time, so that it's fixed. The field values are actually fixed at those points. Okay? So finally, if we put all together, uh, you should be only having, let's see, okay, you should only be getting this part and this part inside inside this okay, inside this variation. Okay, so roughly speaking, what we have in this particular case, everything will multiply your field variations. And this field variation is, again, as I mentioned earlier, is arbitrary. So what is the one that multiplies this field variation? This thing which are, we introduce another notation here, which is really not necessary. No, this is delta L delta phi A, which correspond to your partial derivative of your Lagrangian density with respect to the fields, and then partial derivative of your Lagrangian density with respect to the derivative of your partial derivative of your fields. Okay, together with this total derivative in front, and then also your derivative of your fields with respect to time. Okay, so that is from your second term earlier. This is from your third term. So that multiplies the arbitrary variation, and in order for you to have delta I equals 0 here, then we all need to have this thing to be equal to 0, which is that one, okay, which correspond to the field variations here, which is just like your Euler-Lagrange equation, but now for fields. Again, it seems that time is running out, so I would probably want to stop here. Let me go back to and we'll take your attendance now. Okay, so that's it for today. Are there any questions at this stage? I guess not. So then I will probably end it here. So thank you everyone and see you tomorrow inshallah. Okay, bye.